Okay, so for the last hour, I'll just do two things. So one is graph theoretic, and one is about linear algebra that I will need tomorrow when we talk about eigenvalue interlacing and equitable partitions. Now, one thing I didn't mention, but one way, if you know, I think Godzilla and Royal in their book, they talk about this. Maybe other books talk about it as well. When you want to think about an eigenvector of graphs, so if you have, let's say again, gamma VE, and you have a adjacency matrix of gamma, and you want to, maybe you're looking for an eigenvector, or you're looking for an eigenvalue. How do you think of it in terms of the graphs? If the graphs are fairly small, this equation, you can think of it in terms of picture, in terms of and the idea is that you look at this equation entry-wise, and entry-wise, again, let me change the order. It means that for every vertex in the graph, lambda times ux, it's the sum over all y adjacent to x of uy. Okay? So if I'm looking, I'm looking for, again, something very simple. I'm looking for the graph complete graph. Let's say I don't know what it is. I'm looking for some kind of labeling of the vertices u1, u2, u3, u4, u5, such that when I pick any vertex and I sum up the entries on the neighbors and I divide by the value here, I always get the same number. And that will be the eigenvalue eigenvector. So in this case, I mean, I'm cheating a little bit because you all know, like, I can put 1, 1, 1, and the entry here is 1. What are the neighbors? The neighbors are 4, so the sum of the neighbors is 4. You're dividing by this entry here 1, you get eigenvalue 4. Okay? So that's one way you can think. So if you encounter in your research some small graph, and maybe your first impulse is, okay, I'm going to go fire up a characteristic polynomial and give me some, that can work as well. But for some small graphs, you can do something like this. And then the same graph, if I'm looking for some other eigenvalue, I can do 1 minus 1. I can do 0, 0, 0 everywhere. And we'll play with these ideas tomorrow in more general way. But, okay, here, what's going to happen if I pick this entry? The sum on the neighbors is going to be 0. So my eigenvalue could be anything. Okay, so that's not helping. So pick something that is non-zero. I add up on the neighbors. I get a minus 1. Minus 1 by 1. It gives me minus 1. The eigenvalue minus 1. So this one, it will give me the eigenvalue 4. This one will give you an eigenvalue minus 1. And the advantage of doing this is that you can build yourself linearly independent vectors. Because I have 1 minus 1, 0, 0. Well, once you figure out that, you can do 1, 0, minus 1, 0, 0. And you move this, and you're going to get yourself four eigenvectors for the eigenvalue minus 1 that are going to be linearly independent. Now, granted, they're not going to be orthonormal basis. Like, this one, it's easy to normalize. This one, you have to do a bit more work, some Gram-Schmidt and so on, but you understand what I'm saying. So I just wanted to say that because it's useful to play around with example by yourself and to do these things. And yeah, maybe sometimes you feel intimidated, but essentially for adjacency matrix, this is the entry-wise equation is the one that you have to keep in mind when you're thinking about eigenvalues, eigenvectors. Of course, if you're talking about Laplacian matrices and other matrices, this equation is going to be different. So you have to, this one is the simplest one as far as I can tell, because for Laplacian, you're going to have a degree, and it's going to mess you up a little bit more. Okay, so I thought I'd say this. Now, tomorrow we're going to do some serious theorems about interlacing and equitable partitions and all that. So to do that, I'm going to need something something about max-min theorems about eigenvalues. So on eigenvalues. Now this is something when I was a student, it always intimidates me. Even now I have to look it up to get the details. So let's go through it slowly and to understand what's going on, and then you know, this will be the main topic for the rest of the. So we have again, let A be a real and symmetric matrix. With eigenvalues lambda 1, lambda 2, lambda n, and corresponding orthonormal eigenvectors u1, u2, un. Okay. So before, let me fit it here. Before, we just saw something of the form lambda 1 was the max over all u in Rn, u non-zero of u transpose au divided by u transpose u. Okay? And once you normalize, you do the same thing with norm 1, but I'm not gonna. And you can, from the same proof, you can get the obvious thing that lambda n is the minimum over all u in Rn of this Rayleigh quotient. I'm sorry. Okay. So lambda 1, lambda n. So what makes them so special? Well, lambda 1 is the largest, lambda n is the smallest. What about some ones in the middles? Can you characterize them like that? So that's what I will tell you now. So to do that, let me step aside here and kind of go through this a few things a bit slowly. So you have A, you have lambda 1. Let's say I have here some, let me go from here. Lambda 1, lambda 2. I have lambda j here. I have lambda n, and I have u1, u2, uj, un. Okay? So, in some sense, so this is how you can remember what we're going to do in a second for general lambda j. So lambda 1 is going to be the largest, so it's the largest in this sequence, so it's going to be the largest of the Rayleigh quotient in the space spanned by everything, which is Rn, which is the space spanned by u1 all the way to un. Lambda n, again, because it's at the end of the spectrum, is going to be the minimum of that. Now, what I want to say something about lambda j. Okay? So for lambda j, is going to be a little bit, that's where we're going to have this max, min, max, and you always, okay, which one do I go? How do I sort it out? So for now, I will have, this is going to be capital Uj. So this will be the span of U1 all the way to Uj. So you see, like if you are in this span and you take a vector from here, and I'll write it down in a second, and you look at the Rayleigh quotient, lambda j loses because lambda j is the smallest. It's the smallest in this set. And then we're gonna I'm gonna look at a different subspace, which is gonna be like this. Let me see how I denoted in my notes. Well, if this is Uj, this is going to be Uj minus 1 transpose. So it's the one from Uj. So from Uj, when you're in the middle of the pack, you can look up and you can look down. So Uj is going to be here, and lambda j loses in this set, but lambda j wins in this set. Okay? So now, again, exercise, how much? 12. Exercise 12. if I take the minimum over all vectors u in uj, u non-zero, of u transpose au divided by u transpose u, what do I get? Lambda j. Okay? So that's part one. And then part two, I look this way. If I look at the maximum of, I don't know, let's say V, V transpose AV, V transpose V, V transpose V, no V transpose, V in uj minus 1 transpose, perp, sorry, perp, V not 0, this is also going to be lambda j. Okay, so in some sense, what we saw here, it's kind of like something that is just happens for lambda 1 and lambda n, because lambda 1 can only be the maximum of everybody. Lambda n can only be the minimum of everybody. Here, lambda j, if you look from two perspectives, if you look up, lambda j is the smallest. If you look down, lambda j is the biggest. So that's kind of like, with that perspective in mind, lambda j is going to be the minimum of the Rayleigh quotient over this space, and it's going to be the maximum over this space. So this is the same proof that we did before. I'm not going to do it. Okay? Okay. So, okay, why am I telling you this? Because now we're going to write, so lambda j is already the minimum of that. Then, okay, eigenvectors. Then, 1. Lambda j is going to be the maximum over all subspaces W of Rn with dimension of W equals j of the minimum of let's see if I get it right. Minimum of u contained in W, u non-zero, of u transpose AU. Okay, so that's one part. And I don't know if I'll fit the second part under it. So, let's try 2. Lambda j, you can write it in two ways, but okay, it's going to be the minimum. Do I have it? Minimum over, let's say again, W in Rn, dimension of W is j minus 1 of the maximum over u in W perp, u not 0 of this Rayleigh quotient. Okay. Which one? Dimension.
N minus j plus 1.
No, I'm fine. I think.
N minus j plus 1. Perpendicular, orthogonal perpendicular.
Where are you? I don't.
Here you see.
Okay.
uj minus 1 plus.
Okay. Yeah. But uj minus 1 is this one. uj minus 1 perp is going to be of. Is going to be so uj minus 1. The dimension of uj minus 1 is j minus 1, and the dimension of this uj minus 1 perp is n minus j plus 1.
Yes.
Yeah.
So the dimension here should be n minus j plus 1.
No. I think this is okay. Well, let's go through the proof and we'll see. Because so the space here, w perp, is going to have dimension n minus j plus 1. Okay. So
Right.
yeah, you can change it from perp. You can remove the perp, but I thought it saved me some time. Okay. So let's just do one, and then I'll leave the two for you. So proof 1. Again, it's a maximum. So kind of informally, you know, you have here the subspaces of dimension j of Rn. Uj is one of them, but there are many other subspaces. Okay. So you have this quantity which depends on w, and what you want to show is that if you take all these quantities and lambda j is going to be the largest of them. So there is a max here, and the reason it's a max and it's not going to be a supremum is here because it's going to be attained for uj. But to show this part, we have to do two things. One, we've kind of already did it, but then we have to do another thing. So one, for any w subspace of Rn with dimension of w equals j, I'm going to look at this quantity minimum of I'm going to look at this quantity, and I want to prove that if I take this minimum, lambda j always beats it. Okay? So if you are the maximum of something, you have to be greater or equal than everybody else, and you have to have some equality. You have to attain equality. The equality part is going to be attained here with uj. You know, that's the equality part. So again, so in order to prove this statement 1, we have to do two things. This one, and there is, so I'll write it like this. There is w subspace of Rn, dimension of w equals j, such that lambda j equals the mean of u in Rn Okay. So if you're the maximum, you beat everybody else and you attain the maximum somewhere. Okay, and this part 2, it's from here. So this will give you part 2. So I won't do that, but I'll quickly go over this. Okay. Okay, for any w, so proof, what do I want to show? I want to show for any w subspace of Rn, dimension of w is j. I have that lambda j is greater or equal than minimum of v in Rn. There is v, u, sorry. Okay. Okay, so what do you have to do when you want to prove that a number is bigger than equal than a minimum of something? What is it?
It's greater than or equal to any of the U transpose.
Not any, it's a minimum. So if I find a vector u, here, oh, this should be in W, sorry. If I find a vector u in W, which is not zero, such that lambda j beats the Rayleigh quotient of that, I'm done. Okay? So I just had to find a vector. So, so that's what we're gonna do. Okay? How do we find it? Well, this is a game of dimensions. It's a dimension argument. So what we have is, because dimension of W is j, and so again, you play the you see like lambda j has plays two roles at the same time. On one hand is the smallest if you view it from the top, lambda 1, lambda 2, lambda j, and on the other hand is the largest if you view it from its down. Okay, so that's kind of you play. So you have this. Now what we're going to look at this uj minus 1 perp vector. We have the dimension of uj minus 1 perp. So uj minus 1 is from 1 to j minus 1, so the dimension of the perp is going to be the rest, so it's going to be n minus j plus 1. You do the usual thing. We have that. The dimension of W intersect uj minus 1 perp is what? Is the sum of the dimension minus the dimension of the plus of the okay. So now what do I have? Dimension of W is j, dimension of this is n minus j plus 1. Minus the dimension of this. But here you have minus, so what I want to, how big can the space be? W plus uj minus 1 transpose. The whole space. So this dimension is less than or equal to n, so if I take a negative, this is going to be greater or equal than j plus n minus j plus 1 minus n. And that is exactly why you took here this, because it's n minus j plus 1, and when you add up, you get more than n, so you get n plus 1 minus n is 1. Okay? So what does it mean? Non-trivial intersection. So there's a non-trivial intersection, therefore there is I call it V in W intersect uj minus 1 transpose W not 0. Okay. I'm gonna I'll erase here. No, I'll leave it. You okay with this? I'll erase it. So now we look at this W transpose A W. Again, it's in the intersection, so it's going to be a double agent. It's going to play two roles for us. Okay, this what do I call it? V. I call it V. Sorry, V. V. Okay. Now, because V comes from the space W, this is going to be greater or equal than the minimum over all U in W. U transpose AU. This is because V belongs to W. And obviously V is not 0. But now the stuff that I erase, because V comes from the space uj minus 1 perp, which one is the biggest number there? Lambda j. So here, because V belongs to uj minus 1 perp, this is going to be less than or equal than lambda j. So for this max-min theorem, it's always, you need to find an intermediate, like this, like I said, it's all about the double agent, like some vector that is not zero, that is going to help you on both sides. And this vector is guaranteed, that's why these dimensions are what they are and so on. This vector is guaranteed in this way because, again, W has dimension j, this space has dimension n minus j plus 1, and you're going to do this dimension argument, and you get this W, and that's how it works. Now for so I think that does the proof, because this proves it proves this part 1. Lambda j is greater or equal than the minimum. So this finishes part 1. And then part 2, like I said, I left you as an exercise. You take here to, you take this U to W to be UJ, and you're done. Okay. So this, like I said, it takes a bit of time. We're gonna recap it tomorrow, because tomorrow I will use this to prove these results about eigenvalue interlacing. It's how you compare the jth eigenvalue of a big matrix with the jth eigenvalue of a small matrix. And this is the tool that's used there. So I figure I give it to you today so that tomorrow you're not going to be saddled with this stuff plus the extra stuff. So this will give you a little bit of time to just think about it and try to write it down a few times and see what you can get out of it. Now I'm not going to go through the proof of this one, but it's going to be the same type of argument. Like for the proof of this second part, again, you break it down into two things. Some inequality, general inequality for any subspace of dimension blah, 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 you do this. And then there is a subspace such that happen. And that subspace, again, you get it from certain like extreme eigenvectors, the ones to the left or the ones to the right. Okay? Okay. Any questions? No? Okay. All right. Okay, I'll leave this here. Let me see what I want to do now. Let's do a couple more things before we finish up. So I'll leave this here again. This is the same one I'll use tomorrow. So here are a few things. I forgot the exercise number. 13. Okay. Okay, the usual thing, if gamma is a graph with eigenvalues lambda 1 all the way to lambda n, again, adjacency matrix, and max degree delta and average degree d bar, then lambda 1 less than or equal to delta greater or equal than d bar. So the largest eigenvalue of a graph is always between the maximum degree and the average degree. And that's one of the reasons. This result is that sometimes when you look at questions about the number of edges in a graph and so on, the size of the graph, like extremal question, maximizing the number of edges with certain property, some people now study something, spectral versions of it, where you want to maximize the largest eigenvalue with the graph with those properties. So now for this inequality, you have two inequalities. I'll let you think about them. Maybe some of them you already know them, so maybe some of you don't. So I'll let you think for 2 minutes, and then I can ask participants. Do we give them maybe more coffee or tea if they come to the board, or?
More albunas.
Oh, yeah. Well, no, because I ate all of them, so I'm sorry. Maybe tomorrow, but yeah. So I'll give it 2 minutes. Just think about it, and then we can, if you know how to solve it, come and do it. If not, we can, and then we can do something else. Okay? So just 2 minutes. So some of them may know, some of them may not know.
Yes,
so
let them try first.
yeah, I'll let them think about it. So yeah. So. Do you guys have questions?
The last step
With of the inequality?
yeah, we are trying to prove there exists some
Subspace?
some vector.
You here? Here?
First, the number one.
Number one. So this is so you have this W which is here and it's also here. So because it's here, you get this. By this, you'll write it as linear combination. Because it's here, this is a minimum over everything in here, but this vector is in there. So this, the minimum is less than. So there's no linear algebra here. This is just the minimum value of a function is less than or equal than the value of a function at some point. So
The first part, lambda j.
so that's what you have to do. So you have to write down, because you see v is in uj minus 1. So uj minus 1 was the span of the first. And uj minus 1. Do I get it right? No. Oh, no. Let me see. Yeah. So uj perp. So here, lambda j. So lambda.
Okay.
But no, this should be the maximum. Did I get it wrong? Let me see. No, it's okay. Because yeah, but so here I'm not doing yeah, so the forget about max or mean. Here I have a vector v from here. I'm going to have a vector v from here. So this vector v is going to be a linear combination of this. So when you calculate v transpose AUV, v transpose v, this thing, lambda j is going to be bigger than you. Because v comes from this set, and lambda j is the biggest. So it's the same as we did lambda 1, lambda n earlier, the same type of argument. It doesn't, because you don't know anything about this v.
Yeah, but on the other side we have minimum and then that is equal to lambda.
It doesn't have to, it's going to be for some subspaces, but it doesn't have to be for all subspaces. Because you see, like we took W to be an arbitrary subspace of dimension J. There are many. It's not going to happen then. So yeah. So try to this one, like you're going to have to write down the proof again and try to see if you can remember it without looking it up. I mean, or the best thing, try to do the proof for part 2 for this one. Try to do the proof of this one and see if you can set it up in the right way, and that's how we can do it. Okay. Any? Oh no. Okay. What is it? Average degree. So the average degree is going to be just the sum, or you take all the vertices and you sum up their degrees and you divide by the cardinality of V. So let's just do a simple example. So the graph that we did a bit earlier, this one, you have like the degrees. So I'll just write on the vertex, I will write the degree of the vertex. So here you have degree 3, 3, 2, 2. So the average degree here, you 3 plus 3 plus 2 plus 2 divided by 4 is 2.5. Okay? And the maximum degree is obviously 3, because it's the maximum degree. So this inequality says lambda 1 is between 2.5 and 3. I don't know what this lambda 1 is here. You know, that's another exercise you can try to calculate. I'll show you an easy way to calculate it tomorrow. But that's basically the result. Okay, so that's what your colleague was asking about. What is the average degree? Okay, so so let's go over the proof of this fact. I'm going to erase here. So there are two inequalities. Let's do them side by side. So let's do first lambda 1 greater or equal than the average degree. So again, because you have this formulation of lambda 1 as a maximum of this Rayleigh quotient, when you have inequalities in which lambda 1 sits on the bigger side, that could be a place where you can apply that. So yeah, you can do, you know that lambda 1 is going to be the maximum over all vectors u in Rn, u non-zero of u transpose AU, this. So that means lambda 1 is going to be greater or equal than this for any vector you give me which is non-zero. So then the simplest vector you can think of is all ones, and you plug, you get that lambda 1 is greater or equal than the all one vector plugged in here. And you're going to get here, you're going to get the average degree. And this is, of course, you can be greedy now, and you can say, well, if I want inequalities for lambda 1, I can apply this to powers of A, I can apply it to polynomials of A, but you have to be careful so that in those polynomials of A, when you apply the polynomial lambda 1, you still are the biggest value. So people have used that, and you can get inequalities involving the power of lambda 1 and the number of walks in the graph and so on. So that's, you can get like here, you apply these inequalities to various functions of A, you get many inequalities. So I'll just show you one. Now the second part, delta greater or equal to lambda 1, here it's useful to think about this type of a view of eigenvalue, eigenvector part. So you can think of, you have AU equals lambda 1 EU1. Now, I don't have anywhere anything about connected, so I don't need to use, I cannot just say U1 is positive, but I don't need that, okay? But I have that U1 is not 0. Okay, so there's some entry which is not 0. Now, what I can do is take x in V such that U1 in the value x, let's say in absolute value, is the maximum over all y in V of U1 y in absolute value. Okay, so then, the value in the eigenvector entry at x in absolute value is bigger than everything else. Then you look, okay, what happens at the vertex x in the eigenvalue eigenvector equation? So let me, I guess we're good with this proof, so I'll erase it here. So from this equation, you have that lambda 1 u1 at x is the sum over all y adjacent to x of u1 y. And you just apply absolute value to both sides, and you get lambda 1 u1 x is going to be the absolute value here, so it's going to be less than or equal, by triangle inequality, summation of y adjacent to x of absolute value of u1y. But which one is the biggest value of these u1s? Right, it's the u1x. So this is going to be summation less than or equal, then the degree of x times absolute value of u1x. You put this over here. And then you can take your absolute value here, and now u1 is not 0, u1x is a maximum absolute value, so this is guaranteed to be positive, and now you divide, and you get something stronger than what I told you. You get lambda 1 is less than or equal than the degree of x, where x is a vertex of maximum eigenvector entry. Well, does x have the I don't know what degree it has, but I know for sure it's going to be less than or equal than the degree of d. Okay? So see if you can build a graph where the maximum eigenvector entry is not at a vertex of maximum degree. See if you can do that. Okay?
The degree of x means for all x, for any x.
For some x. Well, you see, the x, you take an x where the eigenvector entry in absolute value is the maximum. Okay? If the graph was connected, I could have taken an x where u1, the entry is the maximum. I forget about absolute value because I have all entries positive, so I don't care. But in general, you just take one where the absolute value is the largest, and then you write eigenvalue eigenvector equation. And so this eigenvalue eigenvector equation, you see that you have information locally. You have information about the vertex, the neighborhood. You can play a game. You can even look at the second neighborhood, and you can get some extra information there. And people have done that. People have, it's commonly used in some research paper to get information about that. But for now, I think that's good enough. Now, question for you: when do you have equality in these bounds? So here, equality, and why is that? If and only if, or if So when is lambda 1 equal to the Rayleigh quotient of a vector? What does it mean about that vector? It must be an eigenvector. So in that case, for this inequality, the all 1 has to be an eigenvector to lambda 1. And when you write down what it means, A1 equals lambda 1 times the all 1 vector, it means the graph is regular, okay? So, okay, here, equality, if and only if regular. What about here? Somebody said regular, I don't know who. How many people for regular? Okay, one person for regular, two people for regular. How many people to, let's be more careful? What is it?
One component can be a
One component can be a big regular, delta regular graph, and then you can put a bunch of things around it that makes it not regular. So you have to be careful. So here, if in addition I gave you the hypothesis the graph is connected, then it will be regular. But for now, you cannot say. Like you can say something, a component where you have delta as an eigenvalue is going to be regular, but that's about it. So be careful about these things. Don't just jump to, just because. So you have to analyze them a little bit carefully. But you see, it's not super hard. So maybe we'll finish now. Okay. Okay, it's a bit early, but they've been good students, so they need a break.